Yeah. It's probably supposed to feel a bit weird using one of these. But hello, my name is Torben, and I'm employed at Danfoss Refrigeration and Air Conditioning, and I'm going to tell you a bit about the supermarket system as a distributed energy resource. The reason why Danfoss is participating in iPower is basically to gain knowledge that enables us to provide the products for our customers to smart grid enable their refrigeration systems. And the application that we're using is a supermarket refrigeration system, like something like this, which I guess you've all seen, at least from the sales area side, where we have the display cases where you store food, and thereby the thermal capacity which is what we're effectively utilizing over here to sort of switch time shift. I hope that's not something we did. We are utilizing it to time shift our energy consumption. What? Okay. So apparently this noise will be over in 30 seconds or something, I've been told. Yeah, okay. Yeah, I think I'll try to continue now. That was the first. It's the first time I've given a presentation where they decided to try the alarm system. Yeah, yeah, where was I? The thermal capacity resides in the display cases, and out the back we have the compressor system, which uses the majority of the energy in a system like this. The products that we provide from Danfoss is sort of the controllers, the valves, and AC drives and sensors, and that is sort of basically all the components that we need to run the control system, and thereby effectively make use of this thermal capacity. So if we take a look at a supermarket refrigeration system from a sort of more schematic point of view, it's comprised of sort of a condensing unit that rejects the heat to the surroundings. It usually resides on the roof of the supermarket. And then we have a compressor rack here, usually a number of compressors that sort of supplies the flow in the system, and as I also mentioned, is also responsible for the majority of the energy consumption of the system. And then we have a number of display cases with individual temperature controllers. Here we only have 2, and for this to look sort of more like a real supermarket system, we of course not only have chilled but also a frozen set of display cases. Again, in a real life system you would have not only 4 display cases but a lot of them, so what we are faced with here is a quite distributed control system with individual controllers for each of the display cases and each of the compressor racks. And when we then want to do power control of this, it's a problem of utilizing the thermal capacity that resides here to basically control how we manage the compressors. And how does it look? This is the refrigeration lab that we are actually using right now, and it's as Samira mentioned, it's located at our headquarters in Norborg. And as you might be able to see, there is no thermal capacity in all of the display cases. So what we did is that we put in some glycol-filled containers to sort of give us some thermal capacity. It's of course not sort of the optimal solution from a seen from a point of view of mapping the real thermal capacity, but it has some practical implications that made us implement it in this way. Besides that, we of course also have some compressors. We both have a low temperature compressor rack and a medium temperature compressor rack. And even though that some of them are actually controlled by frequency converters so that they can be continuously controlled, most of them are actually on-off controlled, which is why you'll see some oscillations on the power consumptions of the system. And the supermarket as a distributed energy resources sort of has two things I want to talk about. First, the flexibility, and then how we effectively do this power control. It's important to know that a thermal system like a supermarket refrigeration system, the flexibility is highly dependent on both the current state of the system and also the operation condition of the system. For instance, the flexibility will be quite different during the summertime when there is a high load on the system compared to in the winter when there will be a low load on the system. We cannot just force it to consume energy. So, and we can describe that by this, if we look at this curve, which sort of describes the maximum and minimum power consumption of the system, where on the x-axis we have the time to saturation, so the time when the system will need to go back to the baseline. And if we ask the system and yeah, I should say on the y-axis we have the demand adjustment or power adjustment, if you like. So if we ask the system for flexibility with a very long time horizon, then we will only be able to come up with an answer that is very close to our baseline, because we will not be able to that. That is simply if it's much longer than the internal time constants. However, if we sort of come up with a shorter time to saturation that we need from the system, it becomes better, and sort of eventually it will actually go towards that the maximum power consumption will go toward the nominal consumption of the system, and the minimum will go towards zero. However, that's not really that interesting. What the flexibility is in a very short time frame. So what is more interesting is to come up with a setup where we can sort of ask for a particular time for minimum power consumption and another time for maximum power consumption, and that will then and that's actually what we do in the setup, which is why we have this specific time of duration, time of activation and duration for the supermarket system. So the power control is basically done by manipulating the amount of gas that the compressors receive, because they sort of consume the amount of power they consume is based on the amount of gas they have to compress at a given point of time. And the way we then do it is that instead of sort of doing directly control of the compressors, which might be the most intuitive thing, we sort of attack the problem from where the thermal capacity actually exists, which is in the display cases. So if we look at a temperature profile from a single display case, remember that in a real system I would have a lot of these sort of in parallel. the normal way of controlling it is that when we hit the upper constraint of the temperature, we will open the valve, and then the temperature will start. We'll first see a small overshoot, and then the temperature will start decreasing, meaning that we are producing gas from that particular display case, which goes to the compressor, which then consumes the amount of power required to compress that particular amount of gas. And then when we hit the lower constraint, we will shut off the valve and stop producing gas, which will then decrease the consumption of the compressor eventually. And that happens sort of in parallel with all these different kind of display cases. So if we want to sort of decide when that actually happens, what we can do is look at the ones that we have running and see that, oh, this one, we can actually switch the state of this prior to when it would actually happen, and then increase the power consumption. And on the other hand, if we shut it off here prior to it hitting the constraint, we will start decreasing the power consumption. This, of course, only works when you have a lot of these display cases. And then eventually we'll stop doing power control and we'll go back to normal operation again for that particular thing. So important properties to remember from a DER perspective of a supermarket is that, as I think also actually one of the comments from David Hill yesterday was that systems are usually built with a primary purpose, and the supermarket refrigeration system is to refrigerate the stored goods. So temperature security will always have priority. So that is also why the control structure is in this way, that we will always fall back to relying on sort of food safety strategies. And the flexibility, as I mentioned, is really dependent on the current state of the system and also the operation condition. And with this setup, smart grid integration is highly based on existing control schemes that we use. It's reasonable to assume that it can be this strategy can actually be rolled out and retrofitted to older systems. And that was what I had to say about the supermarket system. And now Casper will tell you about the chiller.